So, good afternoon, everybody. So, I would like to introduce my talk by saying that actually I'm going to talk about two things today. I'm going to introduce people to the MSc program in chemistry at Nazarbayev University. And as a second part of our session today, I will give you a short lecture on using nanotechnology in the war with superbugs. So I'll combine something which is like more for orientation with something that is like directly related to the research that is going on, and it will be going on in the Nazarbayev University, especially in the chemistry program. So starting with brief introduction, this university is established in 2010. It's very young and has been around only for 10 years. At the moment, it has more than 500 international faculty, most of them research active, and over 6,000 students, both BSc, master, and PhD students. So it's positioned in the capital, Nur Sultan, and I would like to introduce today the chemistry department and its master program. We are based in the School of Sciences and Humanities, alongside with many other departments. This is the biggest school in the university. And I would like to talk today specifically about one of our programs. We have a Bachelor of Science in Chemistry, but I'm going to talk mostly about Master of Science in Chemistry, which we started in 2019. So we are also expected to launch a PhD program in chemistry next year. I would like to mention that all our programs, including the Bachelor of Science and the Master of Science in Chemistry, are closely aligned with the American Chemical Society and the Royal Society of Chemistry guidelines. So they are very rigorously developed. And basically, with respect to chemistry, I expect some of you who are interested in doing MSc of chemistry, who are already deeply involved in this discipline. But just to mention that chemistry is often considered as a central science. So it has a key role in many other aspects of life and many other disciplines. So it's closely related to, for example, medicine, so education, development of pharmaceuticals, development of novel materials. It's linked to disciplines like physics, biology, so forensic science, novel development like nanotechnology, and many other fields. So that therefore it underpins these different activities in other areas, and it is closely intertwined with their own research platforms and elements as a science. So you may consider at the moment what I'm going to do if I take on this career pathway. If I graduate in MSc in chemistry, what potentially I can work in the future. So there are a lot of opportunities for you. So for example, in chemistry education, you can become a professor and or educator. There are a lot of other universities here in Kazakhstan. So you can become also laboratory instructor. You can be involved in safety and disposal of chemicals. So you can graduate in professions which are related to chemistry and health. So you can become patent attorney, or you can work in medicine, dentistry, in the pharma industry. You can become forensic expert if you decide to specialize. So you can also find job in the industry. There are many industrial positions in research and development departments. There are government laboratories where chemists can find employment, and also many other academic institutions. So including you can become a chemistry teacher. You can be deeply involved in the chemical industry as, for example, involved in the synthesis and evaluation, testing of different chemicals, quality control. You can be involved in risk assessment of different processes, biotechnology. So if you become laboratory technician or research associate in some of these fields, you can work as an analytical chemist, organic chemist, so biochemists and biotechnologists. You can be also involved in the pharmacy, food and agriculture, also many other fields like this, drug testing, environmental, and vice versa. So, for example, in the pharma industry, only this year there was a 38% growth. So there is a lot of space for people who have chemistry degrees in this discipline. So with respect to where our graduates go, the master program is pretty young. We still didn't have any alumni at the moment because we started approximately 1 year ago. But our chemistry programs are very well received everywhere in the industry. And this is a brief example of where people go after they graduate with chemistry degree in different industrial-based employers. So they can work in companies like BASF or can find employment further in the Nazarbayev University as PhD students and scholars and many others. So with respect to the master program in chemistry, so this is a 2-year program which includes 120 credits. So it is very research intensive. So the second cycle program is designed in accordance with the Bologna requirements. So the curriculum contains 4 different types of courses. So it contains 30 credits worth of core courses, 30 credits of electives, 18 credits of communication courses, and the research courses, which involve the master thesis, amount to 42 credits. So this is a glimpse on the chemistry, a master in chemistry program. So what people study in the first semester, we study fundamental courses, principle in physical chemistry, applied analytical chemistry, inorganic structures and reaction mechanisms, also organic chemistry. And in the second semester, you are allowed to take one chemistry elective course. We have a rich selection of chemistry electives from 4 different areas like inorganic, organic, analytical chemistry, and also materials chemistry. So in the second year, you are allowed to take 4 of these 3 electives. You have very wide choice. Each one of them brings you 6 credits. So you also are involved in formulating your thesis proposal, and you work on this research project, which forms the base of your thesis in the second semester. Most people start work early, so which covers basically both semester 1 and semester 2. So if you choose to do MSc in chemistry, the key benefits you can have are fast developing research infrastructures. We are constantly building and upgrading our research labs. So you will have a very well balanced study, so which includes research programs which are delivered by a very highly qualified international academic staff. Almost every one of our academic staff in the chemistry is research active. So these are the typical priority research areas, from design and synthesis of nanomaterials for energy, environmental, and biomedical applications. So it will also involve biosensing, biomedical research, and organic synthesis and catalysis for sustainable technology. So usually our first year MSc students have to choose a research supervisor in the first semester. So then assemble advisory committee and get approval for their chosen research topic, and they continue in the following semesters to work on this project in terms of literature review and start the real work in the laboratory in the second year of their MSc degree. So this is our chemistry team. So we have 16 faculty altogether. We have 1 professor, that's me as a chair. We have two associate professors, Dr. Fan and Dr. Balanay. We have 6 assistant professors, Doctors Bukasov, Kalimon, Utepbergenov, Peshkov, Atabayev, and Adilov. We have 3 postdoctoral research fellows who also teach and do research, Dr. Mulkenova, Karapetyan, and Moon. And these are our 4 instructors, Dr. Isaeva, Pershivko, Ostopko, and Dr. Ostopko as well. So briefly to introduce the team and what they do, me as a chair, I have specialized in materials chemistry. I do formulation science, antimicrobial nanotechnology, some of which I'm going to talk today. I'm involved in projects on drug delivery, tissue engineering, and bioimprinting technology. For example, we developed imprints of blood cancer cells, which are able to attract them from solution. And based on this attraction, we can separate blood cancer cells from normal white blood cells. So therefore, cleaning the peripheral blood of patients with leukemia from malignant cells. This is one of my projects which I very recently developed. We also are involved in tissue engineering. We developed a novel method for clustering of cells, which are used in regenerative medicine. So we developed skin grafts based on pre-clustered human skin cells, which allow us to accelerate the healing rates of this type of materials. So I'm going to talk a little bit more about antimicrobial technologies, what I do in this area a little bit later. So very briefly, I want to show you the other members of the chemistry department staff. Dr. Mannix Balanay, who was one of our associate professors. He has interests in material chemistry, computational chemistry, and environmental chemistry. His projects are related to alternative energy. He works on novel types of solar cells, different environmental projects, and biomedical applications. So his field is underpinned by work on nanomaterials. Dr. Haiyan Fan is also associate professor with us. So he is a physical chemist. He's active in the field of laser-induced fluorescence microscopy. He also has developed new types of nanoparticles called carbon nanodots. And he is also involved in heterogeneous catalysis and different spectroscopic studies, especially for intermolecular reactions in solution phase. So he has developed oxygen reduction reaction catalysts for many processes, and he is extremely active in this area. So Dr. Rostislav Bukasov is assistant professor. He is very active in surface enhanced spectroscopy. He's an analytical chemist. He has recently developed novel methods for surface-enhanced Raman spectroscopy, which allows dimerization and trimerization of nanoparticles labeled with Raman-active materials to be studied. So another member of staff is Dr. Andrei Kalimon, who is inorganic chemist and specializes in organometallic chemistry and homogeneous catalysis. He has interests in catalysis for sustainable energy, different types of activation of small molecules, development of new catalysts for different and onto selective transformations, and organometallic optoelectronic materials. His studies are very interdisciplinary and very diverse. Dr. Darkhan Utepbergenov is assistant professor with us. He's a biochemist. So he has recently done studies on a type of protein, DJ1, which is implicated in development of Parkinson's disease. He has studied how this protein develops different catalytic transformations and the configurations of this protein as it undergoes this type of transformations. Very interesting studies related to Parkinson, one autoimmune conditions for which still we don't have any cure. So hopefully, if you decide to come and work with us, you will be having the chance to work in one of these very perspective areas. Dr. Vsevolod Peshkov, he's assistant professor with us. He's an organic chemist. He is working currently on the design and synthesis, and as well as the characterization of different organic luminophores with many applications. So he has also interests in complex heterocyclic molecules, and especially using multi-component one-pot strategy. So Dr. Timur Atabayev is also assistant professor with us, very research active. He is active in the area of material science and nanochemistry. He has recently developed novel type of functional contrast nanoprobes for MRI applications and as a fluorescent imaging of tissues. So here is an image of cells which have been interrogated by adding this type of materials on their surface, which allows you to image them under different conditions. He is also very active in synthesis of semiconductor nanostructures for novel types of solar cells, for light harvesting and also for conversion of wastewater. Dr. Salim Gireya Adilov is an organic chemist, so he is involved in structural studies of porphyrins for nonlinear optics and host gas chemistry. So we also have our instructors that are research actives. Dr. Olga Pereshivko works on different syntheses of potentially bioactive heterocycle molecules. We have Dr. David Harapetyan, who is also a postdoc with us. He is doing different research projects on electrochemical organic synthesis. So, and Dr. Anara Mulkenova, who is also postdoc with us, he is involved with synthesis of functional carbon-based nanoprobes for MRI and cell imaging. So all of them are very research active. They participate also in the research projects of our MSc students. So they are co-supervised by them, and we really wish that you will have the chance to experience this type of research environment. So with this, I'm wrapping up the presentation of the department with the minimum admission requirements for MSc in chemistry. These are listed on the website of the university. So for people applying to the Master of Science program in chemistry, you must have a BSc degree in chemistry or recognized equivalent from accredited institution. Your GPA must be 2.75 in the scale of 4. You must have an English proficiency. You must present valid IELTS or TOEFL test reports for your application. You also need 2 letters of recommendation, and you need to write a personal statement. So please consult the admissions requirement on the website. I'm pretty sure that our admissions staff will also clarify any additional inquiries in the Q&A session. With this, I would like to move to the second part of my talk today, which is a lecture entitled Using Nanotechnologies in the War with Superbugs. I recently moved to the Department of Chemistry from the UK. I was having a group of about 10 people in the Department of Chemistry and Biochemistry at the University of Hull. Here I'm going to present some of the things that we've been involved with my group in Hull, and the type of research that I envisage to continue to do here in Nur Sultan at the Chemistry Department of Nazarbayev University. The plan today is to talk a little bit about nanotechnology and nanoparticles, to introduce what superbugs are and antimicrobial resistance. And I'm planning to talk about the mechanism of the action of antibacterial nanoparticles and how we can make old antibiotics to work again, So how we can breathe new life into old antibiotics by using nanotechnology. And I'm going to cover one topic that we've been very active in very recently, which is how to target biofilm forming bacteria. So first, what are nanoparticles? Nanoparticles and nanomaterials in general are a classes of material where at least one dimension is within the range between 1 and 100 nanometers. So there are many different examples and morphologies of nanoparticles. What you see here are transmission electron microscopy images of gold nanoparticles, approximately 6 to 8 nanometers in diameter. This is iron oxide nanoparticles, hematite, and these are carbon nanotubes. As you can see, they can be very different in sizes and morphologies. Normally, we manipulate these particles and build structures out of them on the scale of 1 to 100 nanometers. So we do this by using different other materials like cationic polymers and anionic polymers, which are having charged ionizable groups on their backbone, and in aqueous solution can ionize and form a counter-ion atmosphere around them, which is bringing them a certain charge, positive in this case, or negative, depending on the charge which is covalently fixed to their backbone. Typical examples are polyalulamine hydrochloride, which is a cationic polyelectrolyte, and polystyrene sulfonate, which is anionic polyelectrolyte. These materials we use like building blocks in order to arrange these nanoparticles in different structures, or to modify their surface so that they can exhibit electrostatic interaction with other surfaces of opposite surface charge. To give you an idea how big these particles are compared with the typical cells that we work with, so on this scale, on this diagram, we have typical linear polyelectrolyte, which are 10, 20 nanometers. Remember, 1 nanometer is 1 billionth of a meter. Typical globular proteins are 5, 10 nanometers in diameter. Gold nanoparticles can be between 5 and 50 nanometers. Typical bacteria like E. coli or the superbug MRSA are between 500 and 2000 nanometers or 2 micrometers. Typical yeast cell, for example, which is a fungal type of organism, is about 6 micrometers or 6,000 nanometers. And the red blood cells are in our blood are approximately 8 micrometers or 8,000 nanometers in diameter on their ring. So as you can see, there is a lot of scope to attach very small nanoparticles on the surface of bacteria, which allows actually us a way to target these cells and to deposit these particles on their surface, which allows to develop different types of therapies. So with respect to superbugs, so we treat bacterial infections with antibiotics. Antibiotics are a special class of substances which are relatively non-toxic for human cells and also for other mammalian cells, but they have high toxicity against bacterial cells. How do they work? They have different type of action depending on the class of antibiotics. Some of them attack the bacterial cell wall, like vancomycin. So others interfere with the DNA or RNA synthesis inside bacteria. So third class of antibiotics impair the foliate synthesis in bacteria. We have others which attack the lipid membrane and different classes which impair the protein synthesis inside bacteria. When they successfully do this, bacteria die. So we can get rid of this bacterial infection. But at the same time, mammalian cells, including human cells, remain unaffected. So how bacteria resist this? So when they are subject to evolutionary pressure by applying antibiotics to them, they develop different defense mechanisms. So how do they do this? By mutations, which are inherited. Usually these are rare events, but because bacteria multiply in such large quantities, they can have the ability to very quickly screen to a range of unsuccessful mutations and to inherit only the ones that allow them to survive. So how do they survive? For example, some of them have developed special membrane proteins which actively transport antibiotics outside of their cytoplasm. Therefore, they decrease the concentration of the antibiotic inside and doesn't allow the antibiotic actually to do this job. So these membrane proteins are called efflux pumps, and there are a lot of bacteria that have developed them. There are other ways for bacteria to resist antibiotics. For example, they can mutate and change the targets to which the antibiotics are binding. So target modification can happen in the ribosomes, for example, and in DNA and many other sites where typical antibiotics tend to bind. And by doing so, they become ineffective. So one of the nastiest type of antimicrobial resistance is when bacteria learn how to secrete special enzymes which deactivate antibiotics. They practically digest them. And these antibiotics, for example, beta-lactams, can be digested by such enzymes called beta-lactamases, which can be secreted inside the bacteria and outside, extracellularly. So the problem with antibiotic resistance is extremely serious. You've probably heard about reports in the media that are nothing short of apocalyptic. The British Chief Medical Officer, Professor Diane Sally Davis, is on record on BBC saying that we don't have to worry about climate change too much because antimicrobial resistance is going to kill us well before the climate change does. So the reason for this is that bacteria develop resistance against literally all known antibiotics. And the sad fact is that no new antibiotic has been discovered over the last 30 years. I mean, discovered and approved for clinical use. So in other words, the bacteria have had 30 years head start to adapt to the existing antibiotics. And at the moment, we don't have new antibiotics to counteract their ability to adapt. So the projections are that in about 10 years time, 10 million people will die worldwide from resistant antimicrobial infections. Currently, about 800,000 die per year as a result of such infections. So the projections are apocalyptic because this will become routine operations like anti-cancer operations, hip operations, hernia, appendicitis, too risky. So if you go in hospital, you can pick up antibiotic-resistant bacteria, and this infection will be the reason why your treatment will be unsuccessful. So how we can solve this problem? So one way is to discover new antibiotics, but as you see, the effort has been going on for 30 years, and no new antibiotics have been discovered. So one potential way of solving the problem is to try to repurpose old antibiotics, and I can show you how we can successfully do this by using nanotechnology. So for example, we can develop cationic nanoparticles which have positive surface charge and can accumulate in large concentrations on the outer surface of bacterial cell walls. So this can be successfully done for gram-positive and gram-negative bacteria because they have surface motifs, molecules on their surface which are negatively charged, which attract the cationic nanoparticles. So, for example, for gram-positive bacteria, you have teichoic acid, which is a negatively charged molecule. It dissociates, forms negative charges. And on the surface of gram-negative bacteria, you have different types of polysaccharides, lipopolysaccharides and phospholipids which have negative surface charge. So what the nanoparticles can potentially do when they concentrate on bacteria? So for example, they can disrupt the cell membrane and cause a leakage of their cytoplasm and death. They can bind and disrupt intercellular components if they get through. And they can also interfere with the electron transport, which causes electrolyte imbalance and cell death. One other method for interfering with bacteria is when they produce reactive oxygen species, which can also damage the cell membranes and also the intercellular components, including the bacterial DNA. So I want to show you one of our approaches which we developed over the last couple of years or so, which allowed us for us to revive two old antibiotics which have long become ineffective. They have become ineffective across a range of bacteria because they exchange successful genetic information laterally, horizontally, by exchanging circular pieces of DNA, which we call plasmids. So these plasmids contain the gene which they use to either produce efflux pumps or develop other types of resistance. So we worked with the antibiotics tetracycline hydrochloride and lincomycin hydrochloride, which are both cationic antibiotics. They have macrocation, so this is the active part, and come in the form of hydrochlorides. So they both interfere with protein synthesis by impairing transfer DNA to bring transfer RNA to bring amino acids to the ribosomal site. So by doing so, they impair the protein synthesis, but they are pumped out by efflux pumps. So to solve the problem with this, we developed a special type of nanocarrier, which is made of polyacrylic acid, which is cross-linked in the form of nanogels. So we take polyacrylic nanogels and load them with tetracycline or lincomycin, then coat them with a cationic polymer, which allows them to attach to the surface of bacteria. So we do this by taking the nanogel, which has got polyacrylic acid. This is the formula of it. We increase the pH, and because it is slightly cross-linked, it swells, goes from 100 nanometers to 300. And if you mix it with antibiotic like tetracycline, it binds to the carboxylic groups. And then if you reduce the pH, it shrinks and traps the antibiotic on the inside. If you coat with a cationic polymer, which is called branched polyethylene amine, you end up with a cationic particle, which is loaded with antibiotic. So the advantage of these particles is that they can concentrate on the surface of different types of bacteria, both gram-positive and gram-negative, and can bring a very high concentration locally of this antibiotic, which overwhelms their defenses. So simply the efflux pumps cannot cope with such amount of antibiotic on the surface, which otherwise overall is in very low concentration, because the nanoparticles which bring it to the bacteria can be very diluted in solution. So to test this platform, we went to Hill Royal Infirmary and collected patient samples from 6 different types of injuries: leg ulcers, so different types of cysts, burn injuries, and ulcers. So we identified the bacteria inside these infected wounds and did the antibiotic susceptibility test on them to find to which antibiotic they are susceptible and to which they are resistant. So we have a very nice collection of 6 different types of bacteria. So different types of Staphylococcus, Staphylococcus epidermis, Staphylococcus aureus, including one which is resistant to methicillin. And also we have Pseudomonas aeruginosa and Enterococcus fecalis, which are also known for development of resistance against many different types of antibiotics. So if you look at the rings which form around the discs with the antibiotics, which develop on the surface of the gel plates where we grow these bacteria, you can see that when a ring forms, the bacteria are susceptible to these antibiotics, but there are also cases where we cannot identify any ring, which indicates resistance to both lincomycin and tetracycline. So we took zeta potential measurements, which
Dear Professor, sorry for disturbing you, but we are running out of time. So can you please shorten your presentation, because we have some questions.
Just a couple of slides.
Okay. Okay, good.
So we found that the gram-positive and gram-negative bacteria all have negative surface charge, and the particles accumulate on the surface of the bacteria because they are electrostatically attracted. And if you look at the time kill assays, when you apply antibiotic which the bacteria is susceptible, it suppresses its action, but the component of the nanocarrier and also the polymers don't have any effect on the bacteria development. But if you expose the bacteria to the nanocarrier encapsulated antibiotic, the number of bacteria active in the sample drops very, very quickly, so they are very quickly killed. And this actually works across the board for tetracycline, both for susceptible and for resistant bacteria. You can see here even Pseudomonas aeruginosa and Enterococcus fecalis. The time kill curves for the tetracycline encapsulated in nanocarriers of this type are going down very, very quickly, which means that the bacteria are overwhelmed by the nanocarrier, although they are resistant to the free antibiotic. So by doing this, we were able to decrease the minimal inhibitory concentration of all these 6 different types of bacteria about approximately 8 times. So we can kill the bacteria with 8 times less antibiotic, and which allows us actually to reduce the toxicity of tetracycline and lincomycin for a range of patients. But if you apply this treatment to human cells, like on this diagram is presented the viability of human skin cells after 24 hours of treatment with the free antibiotics. You see that they have certain toxicity against the human skin cells, but when they are encapsulated at the same concentration in the nanocarrier, their toxicity is much lower. So we have something that really works. So it preserves the human cells, but kills bacteria extremely efficiently. With this, I'm going to stop here. So I'm going to take a few questions from the audience that may be interested in novel antimicrobial technologies. So with this, I want to thank some of the students that worked with me in Hull on these topics, especially Paul Weldrick, who developed this study with tetracycline and lincomycin, and collaboration with different professors around the world, including Professor Velev in North Carolina, Dr. Skorozov, and Professor Hardman at Hull, and also Professor Simeon Stoyanov from Unilever. So also all the group of students that worked with me at Hull. More information about what we do in our group you can find on my research blog, paunofgroup.org. With this, I would like to thank you for your attention and to also take any questions that you may have, both for the MSc program and for the research talk.
Okay, thank you, Professor, for your presentation. I hope it was very helpful for our participants. We have some questions from our participants. The first one is, let me read it. What are estimated ion exchange capacity of these compounds? Like, I think this question is addressed to you, Professor.
So ion exchange capacity is actually quite big. So we have, if you consider the nanocarriers as polyacrylic acid, approximately 1 in 30 carboxylic groups is replaced with antibiotic. So it's actually it's adjusted, it's bound to antibiotic when they are loaded. So which is quite a lot. So you can have about 12% by mass, by dry mass of the nanogel loaded with the antibiotic after the loading is complete. So which gives a lot of scope for this antibiotic to be concentrated and to be delivered directly on the bacteria cell wall, which overwhelms its defenses. Simply their efflux pumps stop working.
Dear Professor, I think you can stop sharing your screen, so like we can see your face. And yeah, good. We have another question.
Other questions?
Yes. Good evening. Can immune system alone defeat the superbugs contracted from a hospital?
Well, that would be ideal. So, but you have to be vaccinated for this, and we don't have vaccines for most of these bacteria. Also, the bacteria constantly evolve and mutate, so this means that the vaccines may become ineffective. So the problem with these bacterial infections is that, especially in chronic wounds, they not only learn how to resist antibiotics, but also develop enzymes which allow them to digest collagen. And when they do, they find their way towards blood vessels. And when they reach the blood vessels, then a condition called as sepsis occurs, when they undergo explosive growth in the bloodstream and also in a range of organs where they propagate, which causes a septic shock and a reaction of the immune system, which leads to very serious conditions. So, and usually sepsis has a very high mortality rate. So, therefore, it's difficult to kill bacteria once they find themselves into the bloodstream. Blood poisoning occurs, which is really a deadly condition.
Okay, thank you, Professor, for your answer. We have another question from another participant. Since yeast also can develop complete resistance against antifungals, can nanogels address the issue as well? This issue as well. I think our participants are very interested in chemistry.
I'm very glad to hear this question, because we are actually currently working on this. So we developed antifungal nanocarriers, which are able to overcome the resistance of different type of fungi, including yeast. So we've been active in working against the fungal organism Candida albicans, so which is also very widespread in many chronic wounds, which are infected with fungal infections. And this one is especially interesting because it forms biofilms. Unfortunately, because of the time restrictions, I didn't have a chance today to talk about bacteria that form biofilms. Also, fungal organisms can form biofilms, and they are extremely difficult to get rid of. So once they form, the only sure way to get rid of them is by scraping them surgically, because bacteria tend to excrete this type of extra polymer substance, which forms like a slime substance on top of them and protects them against different antibiotics. Fungal organisms and yeasts also form the same things and tend to protect themselves against antifungal agents. So we've been working on with the antifungal agent amphotericin B, and we were able to encapsulate it into nanocarriers and to produce active nanocarrier, which is able to simultaneously digest the biofilm and deliver this antifungal agent directly to the encapsulated fungal cells. So we have a solution for this case, and there is an incoming publication which will come out shortly.
Okay, thank you, Professor, for your answer. Dear participants, please feel free to ask any questions regarding the program or regarding the research projects or regarding the admission procedures. And maybe, Asyam, you can introduce us with some admission requirements.
Yes, sure. Thank you, Aidana. But we have new questions. What criteria should they meet? How can undergraduates do research under your supervision? I think this one goes to Professor. Then after these questions, I can
okay.
Remind the participants about the admissions procedures.
Okay, great. Okay, so Professor, can you answer this question about how can undergraduates do research under your supervision?
We also invite some of our undergraduate students to participate in our research project. So this is usually done by contacting the supervisor directly, contact the professor. So if they have active projects, so they can come into the lab and we can arrange them to participate in such research projects. Some of these research projects, of course, are paid. So we can have them as research assistants. So some of our undergraduate students already work in our labs. So I hope after I establish my lab here and to be able to invite some of the BSc students to also to participate in the very near future.
Okay, thank you. Asyam, I think you can start.
Okay, thanks. So I can start with the amazing news. I would like to share that today is the start date of online registration to apply for the Master of Science in Chemistry program. And the deadline for providing application packages is April 30. And all participants welcome to send the applications. And the package that is required is the following. It's a bachelor's degree diploma and also CGPA of 2.75 out of 4.0. Personal essay when you describe your motivation. Why would you like to do a master in chemistry? 2 letters of recommendation. Both of them should be from academia or maybe from the work experience that is related to your research interests. Another one is IELTS test score of 6.5 with sub-score requirements no less than 6.0 or even higher. And of course, your CV with all brief information about yourself. And after the deadline of the application, the admissions committee will review your applications and will ask you for interview sessions. And the decisions will be notified in early June. So this is like a brief timeline of the admissions procedure. Also, I would like to notice that there is an opportunity for the applicants who would like to do research but may have language proficiency like not very high enough to apply to the main program. So they have an opportunity NUZIP, Nazarbayev University 0-year of master's program. This is a 2-semester full-time intensive English and content course program. This program is provided by NU and it is provided for conditionally enrolled students. So once you enroll to this program, after the completion of NUZIP, you will be enrolled to the main program. Of course, you should also complete the exams, pass all the exams, and then after, yes, you will be granted with the NU grant, educational grant. Another thing that I would like to mention is that applicants who have already earned a master's degree under the Republic of Kazakhstan State Fund are not eligible for admission under the state educational order to the main program or NUZIP. I would like to notice this because this is very important. It's written in our rules, and but you all are welcome to anyway apply for this program and try your best. And So this is like a quick outline of the admissions procedure from my side.
Thank you very much, Asyam.
Now I see a new question. Can biology majoring students apply to MS? Yes, sure. They can apply, and also it will be better to provide, yes, in this case, provide recommendation letters from your professors. And if your bachelor's thesis is related in any way related to the chemistry, it will be like very good. So yes, you should try. Could you tell me where I can see the record of this meeting? Oh, Pirisat, I think Aidana will share this
yes,
link.
Right. We will upload the recording version of this webinar on our YouTube channel. So please track our YouTube channel, and we will send you through an email, if I'm not mistaken, as well. So just wait a little. We have another question for you, Asyam.
Yes, GPA on Master of Science. Yes, there is a minimum GPA entry requirement is 2.725 out of 4.0. I think it's like it's normal, it's standard requirement.
Okay, thank you, Asyam, for your answers. I hope it was very helpful, useful for our participants. And we have another question. Is there a possibility to study for one semester at NU, like Erasmus?
Yes, this one will be considered as an academic mobility program. In this case, if you are right now studying at the university that has international agreement with NU, this will be a very good benefit for your request, and it could be considered as an exchange program. And there is also another option when you apply your documents and choose the courses that you would like to take at NU. Then after the approval of the schedule and approval of the payment options, NU school itself will sign a contract with you. But this will be a paid fee agreement.
Okay, thank you, Asyam. I hope it is clear for Alima.
Yes, Alima, if you have questions, you can contact me or Aidana, or just write your questions. I will be happy to answer them.
Right. Alima is saying thank you. Thank you, Alima, for your question. Dear participants, if you have any questions, please feel free to ask us, leave them through the chat box so we can answer them, because it's a very great opportunity to get detailed information from professor, from the chair of the chemistry department, and from Asyam.
Thank you.
I want to type down the email address of our school, so you can send your requests or questions to this email. And we have a website, the school's website, which is ssh.edu.kz. So you can find all information on our website, and the recording versions of all the webinars of our virtual open house days can be found on our YouTube channel as well. So please keep tracking our social media pages on Instagram and Facebook, and our website as well. And dear professor, we have this question that we get a lot. Please let me read it. It is about like top chemistry jobs, like maybe top 10 or top 5, like most trending or popular jobs.
I think that the perception that jobs are only in chemistry may be a bit wrong. So chemistry, the boundaries between chemistry and other disciplines are blurred. So for example, my research is very interdisciplinary, and by using this type of research, you can actually work in many R&D departments to develop new products, for example, new antimicrobial agents. So you can work in the pharma industry, you can try to pursue this research further in an academic institution by doing PhD, for example. So, or you can actually find yourself having these transferable skills which you develop as a result of working on this project and applying them to many other areas. So, because problem solving skills that you develop as a result of immersing yourself into this type of research are quite universal actually, and you can go and exercise them in many different industries. For example, chemistry graduates are also valued not only for their chemistry knowledge, but also for their numeracy and other transferable skills, for example, data analysis. So in London, for example, there are a number of insurance companies that hire chemistry graduates for analysis of the risk. So the same numeric skills and the data analysis skills that you develop trying to crack a chemistry program, so you can apply this for many other problems, including modeling of risk analysis. So you can work in the city of London, for example. So this is just one example of how skills that you develop as working on chemistry program can be successfully applied somewhere else.
Okay, great. Thank you. And maybe we can talk a little about advantages of our chemistry department, like why should people apply to master's program in chemistry? Like we have such great laboratories and so on.
We have a great team, first of all. The human part is important. So we have a very good team of international faculty. So all of us have interests in complementary areas. So we don't work all in one field. So and our research is very interdisciplinary. So therefore, even if you are not a chemistry BSc student, so if you're a biology student or chemical engineering student, or any closely related discipline, you may actually benefit from exposing yourself to into this interdisciplinary environment. So undertaking MSc means that you will be spending at least half of your time doing research and working on particular problems which are defined by our international and very research active faculty. And you have the opportunity to work on research which actually may result in a scientific publication. So which sits very well on a CV after that. So if your project successfully produced a scientific paper, so this is considered as a great achievement. So also shows that you can undertake successfully a project and you can finish it.
Okay, great, thank you. Dear participants, if we have no questions at all, I think we can finish our webinar because we are a little running out of time. So dear professor, thank you for your time. Thank you for your presentation and for your lecture, introduction lecture. It was very, very interesting. And
pleasure.
Thank you, Asim, for helping with answering the questions.
Thanks, you too.
Right, and I want to remind our participants that we will send you a recording version of this webinar. So please keep tracking our social media pages on Instagram and Facebook and our website, and feel free to send your requests and questions to us and to professor as well, to our professor. They are very friendly, and I'm sure they will get back to you with the detailed explanation to all of your questions and requests. Thank you again. And I think we can finish this. Bye-bye.
Bye-bye.
Bye.